All right, let's begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Pray that you'd help us to use this time wisely, just to wrap up our thoughts on Mission 8 and the homework they have to do. And I just pray again, Lord, that you'd help them as they study for this course and other courses and what remains of this semester, that they would just do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, let me just take a minute or two to wrap up whatever it is I didn't do last time. Shouldn't take long. So we, excuse me, we looked at Green's, first and second and eventually third identities. Proved a good bunch of this stuff. The picture? There was never a picture there. Yeah, sorry about that. All right, these are the calculations that I alluded to but didn't do last time. Anyway, you can look at the notes. What I wanted to get to was this. This is the Helmholtz's theorem, which I think it's important for you to be aware of, because it's an interesting result, and it's nice to be able to say something relatively general about all possible vector fields. That's what this does. Suppose you have a vector field f for which the divergence of f is equal to d. That's supposed to be a scalar, not a vector, obviously, right? It's a divergence, it's a function. Okay, that's a typo there, that's not d vector. And then the curl of f is equal to c. Now that c is a vector field, all right? And we're also assuming that these, the c and this d, they get small faster than 1 over r squared as you go very, very far away from a point, say 0. So in other words, c and d are well behaved. They tend to 0 as you go to infinity. And if you have all that, then you can write the vector field f in terms of the gradient of a potential function u and the curl of what I would call a vector potential w. In other words, every vector field that satisfies these mild asymptotic conditions can be written as the sum of a piece which is a gradient and a piece which is a curl. But it's more than that. In fact, formulas exist to calculate the potential u and the vector potential w. There's a lot of typos in this part of the notes. It's almost like nobody's ever read it. W vector here, there's a vector there, obviously. This vector potential and the scalar potential, in fact, can be calculated from integrating the c vector and the d scalar, which are tied to the divergence and the curl of the initial vector field f. So if you know the curl and you know the divergence of the vector field, and if the curl and the divergence of a given vector field behaves as it goes to infinity, asymptotically goes to 0 in that particular way, then you can in fact integrate the curl and integrate the divergence in this sense, and so construct the scalar potential and the vector potential. All right. This is exactly what I showed you last time as it applies to the electric field and the magnetic field. For the electric field, the divergence was tied to the charge density. For the magnetic field, the curl of the magnetic field was tied to the current density, and that's where the formula for the vector potential came from. They're both instances of this theorem of Helmholtz, and the Helmholtz theorem is derived from Green's third identity, basically. Anyway, that's all I wanted to tell you, just to let you know that this theorem is here for you to think about. It's there. If you're confronted with a question like this is what to think about. So. And I think I've already gone over all the fun facts from the later part. So, again, so like the curl of B, this thing is playing the role of quote unquote C in Helmholtz's theorem. And then because of that, you're able to write an A for which the curl of A is equal to B, like this down here, by just integrating the J. And for other reasons, the E term goes away because that's assumed to be 0 at infinity in this context, but because it's magnetostatic, the E is not changing. That partial E, partial T term is gone. There's these other things called Leonard-Weichert potentials that are for more fancy things, but you know, you cover that when you take junior level electromagnetism here later. So anyway, that's all I have for this, and now begins the official time for you to ask some more questions. I'm sorry? I can do that. If I can do it. It got left out of the presentation yesterday because I put that piece of paper down and then lost track of it, which was fortunate actually because I had just enough time to talk about everything except for this. Somewhat ironically. Yeah, that was theorem 7.9.7 is the Helmholtz theorem, if that's what is that what you're looking for? Or yeah. Something similar to 120. Don't freeze up on me. Here. So we're looking at a spherical shell of radius r and total mass m with constant mass density sigma. Find the moment of inertia of this shell with respect to the z-axis. Sure. So how about this? Let's find the moment of inertia of a conical shell with respect to the z-axis. Suppose that this cone has mass m, all right, and suppose that the mass is uniformly distributed over the cone, all right? And let's characterize it by having a radius, you know, r, the height, let's say, is h, right? For convenience of calculation, I put the origin at its point here, right? So remember what moment of inertia is? It is something that's the rotational analog of mass. We introduced it to calculate the kinetic energy of a rotating body. So we're assuming that the mass is stuck together. So it turns out the reason to calculate this is that the kinetic energy rotational is just equal to I with respect to z-axis, omega squared, where this is the angular velocity about z-axis. So anyway, that's why you'd want to calculate such a thing, among other things. But we worked out that, in fact, this moment of inertia about the z-axis is the integral over the object, right, of r squared dm. That's just a generic principle. That works for volumes, for wires, for laminates, and for surfaces. So for a surface, this looks like the integral, surface integral, scalar surface integral of r squared, sigma ds over for the cone. Now the reason for that is that the sigma is equal to dm ds, right? It's the mass per scalar surface integral, mass per surface area. So far so good? So for this problem, I have to figure out what is sigma. Now for the problem 120, I guess I also have that problem. What is sigma? Did I say sigma has some funny dependence on position, or is it constant? Oh, yeah, it's right, constant. So like sigma is, for this problem, sigma would be m divided by 4 pi r squared, right? Because we know the surface area of a sphere is 4 pi r squared. For this one, I happen not to remember the surface area of the cone, so I'll have to calculate that. Now, so interesting. What is the surface area of this cone? Or what's more specifically, what's ds for this cone? I mean, there's different ways we could go about it. We could calculate the angle of the cone, go back to one of my standard examples and plug that angle in to the parameterization for a cone and go from there, right? We could work it from scratch. I'm kind of leaning towards working it from scratch for the sake of this discussion. So if we work it from scratch, what do we got to come up with in order to calculate surface integrals? We have to parameterize the surface. How do you parameterize a surface? Let's say x of something and something, right? Spherical coordinates. Okay, yeah, I'll take that. So one of the spherical coordinates is fixed on this cone, right? This cone is at some angle, let's say phi equals to phi naught, right? There's some fixed spherical angle, phi, that's fixed, that's frozen out, right? And we can use what you say, rho and theta as our parameters. If we do that, great. The parameterization would be rho cosine theta sine phi naught, right? Rho sine theta sine phi naught, rho cosine phi naught, right? Now, if we're smart, we won't even solve for phi naught. We'll figure out what are the sines and cosines of phi naught and just put those in directly, right? We don't even really need to find phi naught per se. It's helpful to look at this picture like this, right? And what I'm doing is I'm just focusing my attention on a particular vertical triangle which is found right here, right? Like this one. See there, I know that this length, well, I don't know that length, do I? But I do know that this is r, and I do know that this is h, and I do know that this is phi naught. And I also know the Pythagorean theorem, so I know that this is the square root of h squared plus r squared. And once I know that, calculating sine of phi naught and cosine of phi naught, piece of cake, right? So like sine of phi naught is r divided by the square root of h squared plus r squared. Cosine of phi naught is h divided by the square root of h squared plus r squared. Yep.
First, the phi naught was from the xy plane to the line.
No. No. Phi naught is here. This is like not that kind of arrow. This is like one of those. This is basically described by that. It's a labeling arrow. That was not meant to be an angle sweeping arrow. Sorry. It's the standard off the z-axis angle for the spherical coordinates. Okay. Okay, so we got this then. X of rho theta is equal to, what is it? It's a rho cosine theta, b rho sine theta, and then, a and a. and then B rho. Where I'm just decided to call this thing A, and this is going to be B because I don't want to write those a billion times in my calculation because they're a drag. Okay, and then you calculate, excuse me, partial x, partial rho, partial x, partial theta. What do we get? A cosine theta, A sine theta, B, and this one gives me minus A rho sine theta, A rho cosine theta. Oh, I'm sorry, yeah, cosine theta. 0. So now we can calculate what's the normal, right? Because remember, the magnitude of the normal is what? This times d rho d theta, this is ds, right? So I want to calculate what's the normal vector field so that I can figure out what ds is, right? So, okay, so the normal would be the determinant of x hat, y hat, z hat, a cosine theta, a sine theta, b minus a rho sine theta, a rho cosine theta, 0. Let's see here. So for the x component, I get minus ab rho cosine theta. For y, I get what? I get b, well, again, ab rho sine theta. For the z component, I get a cosine squared plus sine squared, and I get a squared rho. Is that it?
The y component wouldn't be the negative because you're negative in the second component.
You're right. I have 3 minuses. I only counted for 2 of them. Thank you. Yeah. Of course, we would have figured that out because we always check our cross product by taking the dot product of what we were crossing, right? So take the dot product of my normal with the partial velocity in the rho direction. I get minus a squared b times cosine squared plus sine squared plus a squared b rho. Yeah, they cancel. Good. Okay, so then what's the magnitude of this? This comes together to give me a squared b squared rho squared plus a to the 4th rho squared square root. Oh, well, that's I am so happy to see the same power of rho squared on both of those terms. Are you? I know I am. Because, so ds then is equal to rho square root of a squared b squared plus a to the 4th times what? Times d rho d theta. Yeah, that probably simplifies. What's a squared and b squared? A squared times b squared is actually what?
R squared h squared over h squared plus r squared minus 1.
Plus what? Plus?
The denominator squared. And then for a to the 4th, it's just r.
Oh, yeah. Okay. Sorry. All right. Now this is squared, right?
Yeah.
Oh, it's for both of them. You're right. Yeah. Okay. So I could have done what? Oh, this is r squared times h squared plus r squared divided by h squared plus, I think I see what Luke is getting towards, So it actually simplifies down considerably. This is really r squared over h squared plus r squared.
Inside the square.
And that's all inside the square root. So in other words,
It's just A.
right. Oh, that's just a?
When you take the square root.
Oh, well, duh. This is the square root of a squared plus b squared times a squared. Duh. Do you see why a squared plus b squared should be 1? Yeah. So I think I found a rather complicated way of doing that. Great. Anyway, the point is we get a rho d theta, which we could again express in terms of r rho d theta over the square root of h squared plus r squared. All right. Now we can find the surface area. So the surface area, integral from 0 to 2 pi, integral from what to what for rho? From 0 to square root of h squared plus r squared. And what we got? We got r rho d theta over that constant, right? Now, thankfully, the r and this h are constants, right? So I can just pull those out, and I've got myself a 2 pi r over the square root of r squared plus h squared. Integral of what? Integral from 0 to the square root of r squared plus h squared plus r squared, rho d rho, which is going to give me pi r over the square root of h squared, r squared plus h squared, times, well, h squared plus r squared. Now, where'd the half go? Did you guys see what I did? So integrating gives me a half. That half cancels the 2. I evaluate the square root in the square function. It goes away. And so this just leaves me with pi r square root of h squared plus r squared. It's not too bad. So that's the surface area of a cone, of right circular cone, of course, of height h and base radius r. Now there's of course a more geometric way of doing this in terms of just taking the cone, cutting it, laying it out as part of a circle, and then calculating the angle defect. But I think it's useful for you guys to see it done in this way, right? Now, that's not the answer. I mean, Danica asked me about this question a while ago. It was not this question. I mean, it was this question, but we're now getting to the point of actually doing the calculation, because now I figured out what? Sigma is m divided by pi r square root of h squared plus r squared. So there we go. Now that is way, way easier in 120, because 120 is a sphere. So the surface area is known. Or maybe you've calculated it already on the test somewhere else, right? Surface area of a sphere is not hard to calculate. All right, now that we have all that, I must be careful not to I guess I really just need the ds, right? Yeah. I am worried to erase things, but I need space. Okay, so I think I can work in here. Okay, so what does this work out to here? This works out to m divided by pi r square root of h squared plus r squared. That's my sigma, which is constant. I pulled it out, right? And then I have to integrate from 0 to 2 pi, integrate from 0 to the square root of h squared plus r squared. And then the question is, what is this r squared in terms of the parameterization, right? Now, that's also tricky in the sphere, because probably in the sphere, you're going to use the spherical parameterization, which is what? It's almost the same thing, right? Except instead of freezing out phi, you freeze out what? Rho, right. You said rho equal to r. But the relation between, but this r is not, this r is from another world, right? This is from the world of cylindrical coordinates. How is r and rho and all this related? Remember? Here's the picture. This is rho. This is r. This is phi again. R is equal to rho sine phi, right? So this is rho squared sine squared phi. Now sine squared phi, but it's sine squared phi naught, right? Because we're on the cone. And then ds, what was ds? Well, ds is whatever it was. It was pi r. Oh, that was not ds. Where's ds? Here. ds was r rho d rho d theta divided by the square root of h squared plus r squared. Now what's sine squared? So I'm going to pull some stuff out here. This is m over pi r. I'm going to make that h squared plus r squared. Combine the two square roots. I'm going to integrate the theta because I can. That gives me a 2 pi. And my sine squared phi naught is what? Oh man, I erased the one thing I needed. Look at that. I've erased. My sine of phi naught formula was like right here. So it's r squared over. Yeah, but sine. I'm doing sine. Sine.
R squared over h squared.
Okay, so we agree. Okay, good. Cool. And then I have to integrate rho squared times rho, which is what? How many rows do I got? 3. So I do 1/4 rho to the 4th evaluated from 0 to the square root of h squared plus r squared, okay? What does this give me? Pi's cancel. I get what? I get 2mr divided by h squared plus r squared squared from the initial stuff. The pi's cancel. I get the 2, the m, the r squared over r gives me r. Oh, the 4. Thank you. Make that a 2 then. And then what? H squared plus r squared square root to the 4th power is just squared. Oh. So it's 1/2 mr. Where's my mistake? Find my mistake for me, please. How do I know this is wrong? It's too simple. No, it's too simple is not the right answer. No, the units for a moment of inertia are mr squared. So it should have something like mr squared should be the answer. That's also true for this problem. I've lost an r somewhere. It is conceivable. No, that makes sense. This is mass divided by area. We've had some awesome sneezes this semester. I'm going to miss them. Let's see here. Man. Where's the R? R. Yes, okay, you saw it coming. I was pre-pirated. Pirate alerted me. Let's see here. Come on, where is it? Oh. These r's should just cancel. It's just that. I kept an r and I didn't cancel. I was in the middle of canceling it. I said something. I lost track of what I was doing, and I left it over. So there it is. Independent of h is interesting, isn't it? Yes.
That would also be a free disk then. Basically,
Is that because it's stacks of circles rotating?
Yeah, I don't know. How to understand this result? That's an interesting question. I don't know. But anyway, I should get back to your homework. Right. So the game plan is you have to understand what is the scalar surface integral I'm doing, and you have to come to terms with how do I write the r squared and how do I write the sigma. You know, is the sigma constant? Is it a function? If it's a function, then there's more thinking required, right? Like, how would this problem change if I said that the surface density was a function, like was linearly dependent on z or something? That would have complicated the integral of the mass, and it would also have complicated the integral. I mean, I just calculated surface area. If density was a function of z, I'd actually have to, you know, well. Okay, I'm saying what if sigma was given? So I guess if sigma was given, I wouldn't have to calculate. I wouldn't necessarily have to calculate the mass. Actually, that would be an easier problem. In some sense, if sigma was just given, we had to figure out sigma in this problem. You also have to figure out sigma in that problem, but it's easy, right? Easier. Other questions? Sorry. Yeah. A what? Flux out of the paraboloid. Sure. How about z is equal to minus 3 plus x squared plus y squared. Let me make it easier. 4. And then find so let this define the surface, all right? And then find flux of f equal to, I don't know, x squared y. No, how about x squared z plus 2, comma 1 through s. And we're assuming this is given upward pointing normal. I can think of 2 ways to do this. Okay, I'm going to show you the first way I'll show you is just the way I kind of expect you to do the problem that's given there. Let me put this away actually so I have more room. So first solution would just be direct calculation from the definition, right? So we want to calculate the flux of that vector field f dot ds, right? So what I do is I integrate. All right, so I guess you have to understand what this looks like, right? What does this look like? Right, and this is the circle of intersection, which would be x squared plus y squared equals to 4 at z equals to 0, right? So we're trying to find, and the normal's like pointing this way, all right? So how do I calculate the surface integral? Directly, I need to figure out what's the normal, right? What's the normal? Basically, I use this parameterization. xy is xy, and then the z is x squared plus y squared minus 4, right? Now, we proved before that this has the normal 1, 1, and then minus 2x minus 2y. This is generically 1, 1 minus fx minus fy. This is the normal from, surface parameterized by x of x, y. So put that into play here. My f was, let's see here, let me write it out one more time symbolically before I put formulas in. F was, but I can't read it for now. X squared. All right, now I'm supposed to dot that with ds. What is ds actually? ds is actually 1, 1, and then minus 2x minus 2y. And then I've got my, my dx, dy. Now I wrote, board's all yucky. I wrote something there that I have to interpret. Do you see what it is? I mean, x is x, 1 is 1. No one ever wonders about that. Not too much. But z, what is z? In terms of the parameterization, what is z?
Function of x and y.
Right? Yes. So x squared plus y squared less than or equal to 4 is the parameter domain. Do you agree? So if you look at what x and y are going over, they're at their largest on this circle, and they're like within that circle. That's the parameter domain. That's what I need to do the double integral over, and this should be, so x squared times 1 plus what? Now what is z? Z is actually what? Z plus 2 is actually what? It's x squared plus y squared minus 2, right? Times 1, and then plus 1 times minus 2x minus 2y. What do we have here? We have the double integral over x squared plus y squared less than or equal to 4. And what do I actually have? I've got 2x squareds, just 2 of them, right? 2x squared. How many y squareds do I have? 1 of them, right? Then minus 2x minus 2y minus 2 over dx dy. How do you do that integral? If you do this integral in Cartesian coordinates, I kill you. I will cause you physical harm. No, I mean, these integrate to 0, right, by symmetry. If you look at the disk, radius 2, it's as much, this is positive, negative, the same amount, right? So by symmetry, you can see that these two terms go to 0. And what we really have is the integral from 0 to 2 pi, integral from 0 to 2 of 2r squared plus r squared cosine squared theta minus 2 times r dr d theta by a polar, substitution to polar coordinates. Now, of course, this gives me integral from 0 to 2 pi, integral from 0 to 2 of, oh, that was supposed to be r squared plus r squared cosine squared theta, sorry. So that's r cubed plus r cubed cosine squared theta minus 2r dr d theta. X squared plus y squared is r squared. But I do. Just look between the x's. No, I don't know. So, of course, this gives us then 2 pi r to the 4th over 4 evaluated from 0 to 2 plus, as I recall, 1/4 r to the 4th evaluated from 0 to 2 times pi, integral of cosine squared over whole cycles pi, and then minus r squared evaluated from 0 to 2 times 2 pi which is what? This is 16 over 4 is 8 pi. Plus 8 pi. Minus only 4? You're right. Thank you. Very good. And what's the last one? 4 times 2? 8 minus 8 pi. Aha. So we have a winner, 4 pi. Yep.
Can you explain again why the minus 2x and minus 2y?
Because if I integrate x over an entire disk where half of the values are positive and the other half are negative, symmetrically so, the two halves cancel, the right and the left, and then y, the north and the south cancel. But with x squared and y squared, things don't cancel. They're just, I mean, I could reduce the integral to like a, double the integral over the right half or something, but.
So really, the only term that goes to the entire integral of x is that it's the r squared.
I think that the 2 survived, didn't it? Like the 1? Well, I don't know. I mean, things get put together. It's hard to interpret what's what. Cosine squared integrates to pi. So sine squared plus cosine squared is 1. 1 integrated over from 0 to 2 pi is 2 pi. But the integral of sine squared and the integral of cosine squared must be equal. So twice the integral of cosine squared must be 2 pi. Therefore, the integral of cosine squared is pi over a whole cycle. Or you could use the double angle formulas, blah, blah, blah. What's the other way to do this? By parts? By parts. Well, sort of. Not a totally unreasonable way of thinking of it. How about this? the integral over the boundary of E of f dot ds is equal to the triple integral over E of the divergence of f dv. What is the divergence of this vector field? You say 2x plus 0 plus 0? Yeah, so it's 2x dx of dv, right? So this is actually equal to the integral of, oh, and that's equal to 0, isn't it? I mean, I could work that out for you. This would be the integral from, I mean, how do I write this? E is the solid, E would be this, guys. It's the whole thing, like, filled in. Right? So how would you write the integral over E? How about 0 to 2 pi, integral from what? How would you capture that in cylindrical coordinates? 0 to 4? Maybe? I think about this for a second here. I know that the z bound should be from 0 is the top bound, and the bottom bound is minus 4 plus r squared, right? I think that would be it. And then you have 2 r cosine theta, and then r dz, dr, d theta. The thing is, the only thing that matters in this whole expression, in terms of the integration, if you look at it, is this and this. Nothing else depends on theta here, and that makes all the rest of this stuff just 0. So if you believe this calculation is right, what's the flux of the vector field? What's the flux of the vector field on the cap, right? We just found out that there's 4 pi coming in this way. So how about the cap? What's the flux here?
4 pi.
What's that mean? That means that there's minus 4 pi down here, right? And so that's why you're right, because the flux we're looking for, minus 4 pi, has to be equal to the total flux, which is 0 by this. So it stands to reason, yes, the flux through the disk is 4 pi. Could you calculate that directly? That would be a way we could check our answer, is just to calculate the flux of the vector field through the disk. But I think I'm out of time, so I'll stop. Thanks, guys.